Start, sir.
Okay, hello everyone. Welcome to this second, live session of the course on adsorption, science and fundamentals. Is it started?
Yes, sir.
Okay. So once again, welcome to this second live session on adsorption, science and fundamentals. In the last, session, we mostly discussed about topics related to the first four lectures, where we talked about the basis of adsorption isotherms. Then we talked about BET, as well as the other, this multi-layer adsorption isotherms. We talked about what is the role of the thermodynamics that play within this adsorption. We also discussed quite a few things related to how equilibrium models can be developed, and then slowly we discussed about the other things related to how these measurements using the BET equipment, details about the its characteristics, and what are the limitations is something that we have discussed. We have also talked about the different this role or the different competing effects that you generally encounter along with the adsorption and diffusion in similar systems, particularly relevant for gas and to some extent also on liquid based adsorption. So these are generally these topics that we have discussed in the last live session. So in this session we will focus more on the analysis of the breakthrough, which is like the week 5 contents, if you recall, about fixed beds modeling, Thomas model, Adams Bohart model. How do you analyze the constant pattern behavior? What about the number of transfer units, solution of the Klinkenberg equation? So these are mostly is something that we started talking about from week 5 onwards. And then in week 6, we discussed related to this pressure swing adsorption. So, what is the background of pressure swing adsorption? How, what do we mean by the Scarstorm cycle? What is the cyclic operation? How you can, what is the role of the cycle time? How it can be, how it does play a important role. How this system can be designed. What is the limiting, criteria? How this can be actually be used to make continuous operation using a dual exchange mechanism, or in some cases you can also have multiple exchange mechanisms. What is the mathematical background or the conservation equations that is applicable in pressure swing adsorption system? And then we talked about a sample situation about the model of this medical grade oxygenator. Right, so medical grade oxygenator, as you know, is widely popularized during the COVID pandemic for use of these instruments to produce medical grade oxygen in portable household units. Right, and this works on the principle of pressure swing adsorption. The adsorbent is the lithium exchanged, zeolite, and that is something is very efficient for removing nitrogen from air, and in the process you get a very high quality this purity of oxygen, which can meet the medical standards and is something that is helpful for the patients having respiratory distress. Now, following on in week 7, we talked details about the chromatographic principles. How the chromatography is widely used in the pharmaceutical industry to obtain ultra high purity of the chemicals or the drug formulations that is produced, and not only that, selective extraction of certain components can also be achieved by this chromatographic separation method. So the principle of chromatography is also based on adsorption, but then it's a kind of fixed bed adsorption. But there is some differences, or some operational distinctions, I would say, that is present with respect to a classical fixed bed adsorption theory. So this is something that this chromatography. That's why the chromatography is slightly different from the classical fixed bed adsorption. But again, the principles and the methods for adsorption and all is more or less same. So there is something known as this illusion or a eluent phase, and something known as the the stationary phase. So the stationary phase is nothing but the fixed bed or the adsorbent, and the eluent or this mobile phase is nothing but the solution that is flowing into it. So this mobile phase or the eluent will actually contains the solute or the solute mixtures that you want to fractionate or separate. Now, based on the binding efficiency of, or the relative binding efficiency of different molecules with respect to this the adsorbent that is present, this chromatography can be can be a highly selective process in fractionating multiple different components from a single solution. So it is very important. I mean, the technology that has been developed, and there are several variants of this chromatography. For example, something known as column chromatography, something known as this pulse chromatography. Then you have the this continuous systems. For example, the simulated moving bed. Even though we didn't talk too much about that, but that is something which is also does exist. Now, the interesting criteria is that in chromatographic solutions, since the concentration of the solutes in the mobile phase or in the eluent is very low, this follows the adsorption behavior generally follows the Henry's theory or the Henry's relation. So, what is this Henry's relation? It is actually the the linear part of the Langmuir isotherm. So if you try to see the Langmuir isotherm, which is like initially it has a linear profile, and after that it becomes like a exponentially saturated shape, which takes a form of a plateau or something like that. So in the low concentration range, right, this plot is linear. So if you try to recall the adsorption isotherm equation at low concentration, the denominator is generally very small with respect to that constant, right? 1 plus something is there, no? So that 1 plus some concentration functions are there. So that concentration dependence at the denominator is like very insignificant, and hence denominator becomes constant, and essentially the entire equation, Langmuir equation, gets converted to a linearized form. So the rate of adsorption is proportional to the concentration. That is what is Henry's law is all about. So now, most of these theories of this chromatography is actually based on this Henry's relation, and of course there is a simplification, but that holds very good. So we talked about how the shape of the chromatographic output, or that whenever you do a pulse chromatography or you inject a certain quantity for some time, then the output also has I mean, there is also a pulse output. So it's very similar to the tracer experiments that in reactors. That is something to be done for to study the resistance time distribution and all. It's the same kind of phenomena. If you do a pulse input, if you do a step input, the kind of output profiles that you get is also, I mean, the functionality or the shape of the output curves also follows the same behavior. Now, of course, there is a possibility of peak broadening in most of the cases. That is because of the mass transfer zone, and that is heavily dependent on the particle size, which affects the dispersion of these molecules. So the role of mass transfer is very significant in this column chromatography, and many a times if the mass transfer zone is too wide or the diffusion effects are quite stronger, then you are supposed to get peak broadening, or which is not very desirable, right? Higher is the peak broadening, or the width of the peak, it is not something that you would like to have. It's not something desirable, because it reduces the peak resolution, or this capacity to resolve two simultaneous solutes. So peak broadening is not something that one would actually desire for. So in the final week, next, I mean, this is all about column chromatography. We talked about some problems related to continuous operation, about column chromatography, what about solutal frontal velocity and purging and all. So following in the last week, we talk about this ion exchange. So ion exchange process is the only example where you get a very close relationship with adsorption based mechanisms being applied in the context of reversible chemical reaction, right? So in the ion exchange, it is essentially a chemical reaction process, because in this ion exchange you actually produce some new compounds, right? That is one of the fundamental difference between adsorption and ion exchange. Adsorption generally does not produce new compounds, but in the ion exchange you do produce some new compounds. So in an absolute true sense, ion exchange is not is not an adsorption process. But then again, the principles, the behavior of this equilibrium ion exchange process is same as the adsorption, and that's why generally this is studied along with adsorption process. So the mechanism, or the selectivity coefficients, the separation constants, etc., can all be related to the these coefficients that is present in the adsorption isotherm and the equilibrium model. So that is one of the fundamental basis or the analogy behind the study of ion exchange in the curriculum of adsorption. Now, here we did talk about, the basis, since it's based on the irreversible chemical reaction. We did talk about, the chemical stoichiometric balances, about rate constants, how do we write equilibrium relations, and how the equilibrium coefficients are actually defined. That is something that has been discussed extensively in this week. We talk about the different types of ion exchange regime, when to use an anion exchange regime, when to use a cation exchange regimes. And since these resin operations are highly selective, they are used heavily in producing deionized water, mostly I would say. They are also used to some extent in remove these ionic salts from certain solutions, where particularly it is not so easy to operate the solution or to separate the solution using reverse osmosis based system, which is one of the industry standard for separating salt solutions. In that case, ion exchange is also preferable. It is also used, so there is a heavy competition in the market between ion exchange and reverse osmosis process, but ion exchange is still preferable because it is selectively removing ionic species from your solution, and it does not have any impact or action on the non-ionic species. Whereas in reverse osmosis, that is not true. So it is more of a size-based separation, or separation based on the solution diffusion mechanism, where it also prevents non-ionic species also from filtering out or from separating. So this ion exchange process is widely used for controlling the pH, the electrical conductivity of the water, and almost in any deionized water purification system, ion exchange is a very common process. It is also used to treat boiler feed waters, because so as to reduce the salt level, or the ionic conductivity of the solution, which is something that is very dangerous, or something not desirable to be present in boiler feed waters. So we talked about this an illustration about what exactly, how to work out the ion exchange ratios. What do we mean by the milli equivalence? What about the divalent and the monovalent balances and all? And then we talked about the cyclic operation of the ion exchange. How do you do a first cycle about of ion exchange process, then the this regeneration, and during this regeneration you have this intermediate phases as loading, sorry, displacement, washing, and then finally going to regeneration. How does the shock waves are getting more shock waves are created when do you get a diffuse wave, is something that we also talk about in this class, or in this week. So yes, so adsorption is, and with this ion exchange we actually close this course on the adsorption. There are some other topics related to adsorption, slightly more advanced, which is something that we have not covered in this course. For example, this simulated moving bed, continuous adsorption, continuous this chromatographic systems, or uh, temperature swing adsorption besides pressure swing adsorption. So these are some of the things which is not covered in this course, but nevertheless, I think with the adequate understanding from this course, you are well equipped to handle, as well as to know about these other topics yourself too. So we will actually now take up your questions or any doubts that you have, any clarifications that you want to get, mostly from the weeks 5 to 8. That is what the major objective of this second live session, and we can discuss them now, or if there's something that you want to come up with later on, you can drop a message in the the chat forum, and we'll try to answer them and explain them as much as we can. So yes, now I think the forum or session is open for your questions, your feedback, your inputs, your clarifications, or some more information. If there's something that you'd like to have from our end, we are open to that.
স্যার কি শেষ করলেন?
Yes.
স্যার আপনি কি শেষ করবেন এটা?
না না, শেষ করিনি।
ঠিক আছে, ওকে।
I believe those of you who have came late, I believe this course has been really useful for all of you, and I sincerely hope that you have got a lot of insights into the world of adsorption and its principles and its use, its practical applications. I also do know that the from the assignment questions, it is quite likely that opens up new thought process within you, or something that encourages you to take up this course, or take up this branch of study in a much more depth, and you can something find something which is useful, relevant, from the application perspective, or from your something that you are doing or working with, where adsorption is uh, very instrumental in bringing some change or advancements in the existing process. So mostly, if you try to see the from the application or from the operation perspective, there is one section where on the liquid side separation, where adsorption is heavily used. There is another section on the gas-based separation, where again adsorption is widely used. So pressure swing adsorption, then you have this thermal swing adsorption, and all these are mostly for gas-based application. Chromatography ion exchange is all about liquid based, mostly liquid based separation. So application of gas-based absorption is, I mean, many of you were from industry backgrounds. You will already know that it's widely used for separation of hydrocarbon gases, separation of CO2 capture. Carbon monoxide is something that is also very relevant, and there are many operations in the petroleum, petrochemical, steel. Then you have in the cement sector, as well as in the oil and gas sector, where adsorption is heavily dependent on one of the proven technologies. In the case of the liquid separation, in the case of water treatment, ion exchange process, then you have this chromatography. Chromatography is one of the biggest, market share of the adsorption technology. The liquid-based adsorption are more relevant, and I would say is more something that is widely used, and it has a lot of impact and relevance in the community, as well as in the market demand for its application. So adsorption is strong. Adsorption has strong competition with membrane separation. So there are certain areas where, of course, membrane separation scores higher than adsorption-based methods, because As you know, membrane separation is a rate-based adsorption, sorry, rate-based separation process. So it is generally fast, high throughput, high capacity, but in terms of selectivity, adsorption is more selective. So in general, any equilibrium-based process you will see is more selective, and but the throughput is very low. Whereas any rate-based process is that you will have high throughput, high flux, but the selectivity is very low. The adsorption scores much higher in terms of selectivity aspects, or precision in separation, finer molecules. In fact, it is possible to separate, these stereoisomers in chromatographic systems using suitable adsorbents, right? So there's something known as, chiral separators. If you look into some background reading online, you will find that chiral separators do exist, and chromatography is one of the proven technologies to separate two chiral molecules. In fact, so that is the kind of precision that we're talking about in terms of the molecule from the molecular, perspective, its shape and its structural features. Yes, so I think we will try to take up some questions. If you have anything, please feel free to post it in the chat group so that I can discuss, go through certain aspects that you find it difficult or need some more additional explanation. That is the whole purpose of this live session, and we'll try to take advantage of that. Those of you have joined late, this is the final live session for this course. I believe the lecture materials are all over. I really believe you have enjoyed the this course, and you have learned and gained a lot of insight about the science of adsorption and how this is put into practice. What are the technicalities, the challenges, the theories behind it, how you can design a fixed period adsorption systems, how to interpret the isotherms, how do you characterize your adsorbents, how do you do this breakthrough studies, how do you do this application like swing adsorptions and chromatography, as well as the ion exchange process, which is some of which are state of the art technologies in the present world. Are there any questions in the forum? No. So we can wait for some more time. How many? So we can wait for some time. I also hope that all of you are working on the assignment problems seriously and sincerely, as these problems are framed keeping in mind that you also gain a lot of information, as well as this motivation to work out the problems and learn from something on it, and that can also you know inspire some more background reading about the topics, as well as the state of the art. Um, the exam will be held sometime later this month, and I think all of you are already notified for that. So the examination problems or the questions will be based on mostly what has been taught in the class, in the online lectures, partly from the assignment problems, and of course there will be some open-ended questions for you to think and answer them. There will be both numerical type as well as theory type questions, where you have to pick from the objective options, either single option or multiple options, which may be correct as appropriate. For the numerical questions, you have to work out the solutions, which all can be done with hand calculation and using the online calculator that you will be provided during the exam at the center. It can all be worked it out there, and you can write down your final numerical value of the answer in the question there in the online uh, platform. Regarding the books, I think I already have discussed about the different books which are applicable for this course, and there is something that you can refer to from this about this course. There are various such books. I think in the last live session we have discussed or we have shared with you the information regarding the books. So please follow them. Please look into them. There are a lot of information as well as principles which are discussed there. A lot of example problems which are present in some of the books, which is something that you can find it. You can find them to be useful for this course. I'll just quickly see if I can show you the name of the books once again for those of you who missed the last session. So mostly the name of the books are already mentioned in the website or in the course web page. So if you just go through them. So, for example, the books for the adsorption that are quite I would say the recommended books for studying this topic are this book by Cedar and Henley. So, separation process principles and applications. Then you have this book on by Chi 10, which is actually a very nice book for adsorption, isotherms, multi-component isotherms, and related things. Adsorption calculations and modeling by Chi 10 Tien. Then we have the book by Douglas Ruthven, which is again a very nice book to study for this fixed bed adsorption problems. Of course, the book by B.K. Datto on mass transfer and separation also covers a lot about adsorption, and we have nice coverage about chromatography and this ion exchange processes. Then there is another book by P.C. Wankat, which also covers nicely about the fixed bed model, particularly the Klinkenberg equations, constant pattern behavior. It also does cover very nicely on the this chromatography as well as the ion exchange processor, and there are a lot of nice solved examples, which can be something that is very relevant. So the book by P.C. Wankat on separation process engineering is something that is also can is useful, or something that I can recommend to all of you for background reading and as a reference book. So separation process engineering, including mass transfer analysis by P.C. Wankat, is as a book that has a nice section on adsorption. So I think if there are no more questions, we may close this session. I wish you good luck for the examinations. I also wish you good luck for your career. If you feel that there is something which you are facing, some problem in related to adsorption or related to its principles, we are always welcome to talk to you. I mean, please feel free to talk to you even after this course is over. Just drop us an email and we'll be happy to talk about your problem, to help you, or to provide some guidelines about how the problem can be handled or how it can be improved. It could be related to your process, it could be related to your academic project or whatever. So we are always there, and we always would like to be in touch as well as get connected. I think we may now close the session since there are no questions. If there are any questions later on you find you need to ask or you need to get it clarified, please drop an email to the TAs or to me, or you can also write in the forum which you have, so that we can try to provide some answers or clarify your doubts or your questions. The forum will be active till the I think till the publication of the results. So with this, I think it is time to close the session now. Wish you good luck in your career and do best in whatever you are currently engaged in. So thank you. I think we'll close the session now.
सर सुनाई दे रहा है सर? हेलो?
Yes, we can close the session.
ओके सर, एक्चुअली नेटवर्क प्रॉब्लम છે.
Disclosed.